Do you remember the fun game that we played back in week 4? Have you been playing it obsessively ever since then? I'm sure you have. Let's remember how that game worked. The game worked by picking a positive integer n, and then we thought of all the ways that we could write n as the sum of positive integers. So that was called partitioning n in the language of math. And we looked at all the different ways we could do that, and we tried to come up with a partition that gave the greatest possible product. So you remember we started with the number 8. We wrote a lot of different ways of partitioning 8 as the sum of positive integers, and it turned out that the best way to write 8 was as 3, 3, 2. That was what gave the greatest product. 3 times 3 times 2 gave us a product of 18, and that was the best that we could do with 8. We moved on to 9, and it was 3 plus 3 plus 4, gave a product of 27. We moved on to 10, it was 3 plus 3 plus 4, that gave a product of 36. But then 11 did not turn out to be 3 plus 3 plus 5, as you might have guessed from this pattern, which 3 plus 3 plus 5 gave a product of 45. Rather, 11 turned out to be 3 plus 3 plus 3 plus 2, which gave us a product of 54. And then we continued to look for the pattern, and we saw this. It was always a bunch of 3s, and then either a 2, or all 3s, or a 4 at the end. And for example, we looked ahead at 60, and we said, okay, 60 would be all 3s, and then 61 would be all 3s and a 4, and 62 would be all 3s and a 2 at the end. And the big question that I asked you to think about was, why 3? What was so special about the number 3 that we were trying to pack in all sorts of 3s instead of all sorts of 2s or 5s or 7s, which is apparently everybody's the most common favorite number? What was so special about 3? Now that we've been studying calculus, I hope you recognize that this, in fact, is an optimization problem. We're trying to find the global maximum of this product for any given integer n here. So there's one little, we're about to use calculus, of course, to solve this, because now we know how to use calculus to do optimization problems. There's one piece that you have to take slightly on faith here, but I think you should not be reluctant to do that, which is that the best thing to do is to break this up into pieces all of the same size. So do you remember the very first optimization problem we did? That was the one with the farmer who had 1,200 meters of fence, and she was trying to make a rectangular pen for her animals. And it turned out that of all the different ways to all of the different rectangles, the one that gave the greatest area was what you had probably guessed, a square, meaning making the sides equal to each other. You can do the same thing in 3 dimensions. Of all the different, for a fixed surface area, of all the different shaped boxes, the one that's going to get the greatest volume is a cube. And in fact, you can continue this even into more dimensions, like 4th dimension and so forth, which we can't try to draw on the chalkboard or anything like that. But trust me, the same thing ends up working out. So therefore, it's not much of a leap to say that the best thing to do is to try to partition this into pieces of the same size. So we're going to take our number n, and we're going to break it up into pieces of size x. So for example, here in 60, we could break it up into pieces of size 3. There'd be 20 of them. We could break it up into pieces of size 5. There'd be 12 of them. Pieces of size 10. There'd be 6 of them. So what we're going to do is this product, p of x, is a bunch of x's all multiplied together. How many x's are there? How many times am I multiplying x here? Well, so for 60, if I break it up into pieces of size 3, meaning x is 3, how many pieces are there here? I hope you're saying 20, because that's 60 divided by 3. And if this had been pieces of size 10, you'd be breaking them up. There would be, pieces of size 10, there'd be 6 of them, because 60 over 10 is 6. So there are n over x times here. We're multiplying x by itself n over x times. But going back to the very first week, we have a shorthand way of writing this, right? We write this as x raised to the n over x. So this is the function we want to maximize. Now, we know how to do this using calculus. In fact, what technique, you should ask yourself now, what technique of integration, of differentiation are we going to need to use for this? But before we do that, we have an applet for you to explore this on a graph. So in the applet, you will be allowed to choose the value of n, and you'll be allowed to vary x. So please go ahead and play with this applet and see if you can come up with what the best x is, say for n equals 8, and then change n to 9 and 10 and something, and see if as you change n, does x change or does x stay the same? And then once you have found what this x is, see if you think you know why, what's special about this particular x. Then we'll come back and do it all using calculus.